on this computer. Let's start that over again. Okay, so what I'd like to say is if you have not signed up for a remote exam, there's only 2 people who have done so. You need to send me an email immediately. And the exam is tomorrow if you are taking the exam remotely. And you will be expected to be there. What is tomorrow, Wednesday? You'll be expected to be in my Zoom at 1:30 p.m. And if you're not, you've missed the exam. 1:30 to 2:15. Okay, because only 2 people have signed up, and I'm not expecting all the rest of you to be here. What is that? Zach. So Zach, you have not signed up for, you have not confirmed your in-person exam yet, but you know when it is. So maybe you're a 3rd person. Okay. Let's see. What have we got going here? Lab 4. We're going to continue that. Dr. Cambo comes in. Exam is Thursday or it's Wednesday if you're doing it remotely. If you're not there, you've missed the, if you're not there on one of those times, you've missed the exam and you have not made prior arrangements with me.
Did you say something to me when I first joined?
Yes, I said, Zach, I think you signed up for an exam, but I may not have gotten a confirmation from you, but that's okay. If you're there tomorrow, I'll let you take the exam.
Yeah, I should be there tomorrow around 1:30.
Okay, that's perfectly fine. So now we have 3 people signed up for remote exam. I'm worried about a lot of you. Okay, so this is from IEEE Spectrum. This is how transistors have evolved. The current technology here, I don't have a picture of it, is called a nano sheet, but Dr. Cambo will show you that. It's basically a wider version of this nano wire. The nano wires didn't work so well. They thought they would theoretically, but they didn't really. Couple of little things here. A dielectric, remember silicon dioxide is obsolete. The planar transistors in the Cedra-Smith book are obsolete. The real oxide for about from 2007 to probably 2020 has been hafnium dioxide, or hafnium oxide, I should say. And it has a 4 to 6 times greater dielectric coefficient. The Miller effect is something we haven't talked about yet, but this is a good thing to keep on the top of your head and won't be on the exam. But there's a gate to drain capacitance in a MOSFET that's going to really make the frequency response not as good as BJTs. And that's called the Miller effect. If anybody asks you why MOSFETs are slow, you can just say the Miller effect and it'll sound like you know what you're talking about. We'll go over that in gory detail. Yes?
Did you say that that will or that will not be on the exam?
That's not on the exam, but you'll hear it in Dr. Cambo's lecture. It's like every year he pauses and he goes, do you know why MOSFETs are slow? And everybody goes, no. And I go, you haven't done the Miller effect yet. But if somebody says the Miller effect, I'd be amazed. The butterfly effect, something like that. Okay. This is exam 1. Oh, never mind. This is exam 2 review. Be grateful this is not, this time last semester, you were taking your first exam in here and it was over everything you've covered so far. So thank goodness, be grateful for a second exam. You get 2 note sheets, formulas written on it, front and back. I highly recommend one of those sheets be your sheet from exam 1 because it has things in there like Km prime and calculating currents that you may have to do on this exam. You can use a calculator. Ruler might be helpful. No other electronic devices other than your laptop. I could just blow out the water. There are, how many problems total? I don't double check that. There are, there's no question marks there. There are 7 real problems, and there's some extra credit. There's more extra credit than that. Okay, and I've got the exam sitting here right in front of me, or the key. This is what's written on the front page. If you need a threshold voltage, it's on the front page, the N-type, the P-type. You need a K and prime, it's on the front page. You need a lambda that's in units of per volt. It's on the front page. You need gamma for the body bias coefficient, that's there, so's phi f. My VDD's there. The minimum L of a transistor is there. You can use that as you want to, and some other parameters here. You can use those on any problem. If you see silly questions on the exam, please answer them. They are worth a point. And your quest is also worth a point. It's your goal, not mine. Don't ask me what my quest is. It's a free point if you fill it in. It could be anything you want to write there. I've taken a lot of them that just don't make any sense to me. It's worth a point. So the stuff we've covered so far, the DC bias circuit, so being able to calculate the DC bias point is kind of crucial, and it does show up. Calculating DC bias points, ID, it's on problem 2. Calculating a DC bias point, you've got to do some of it on problem 4. You've got to calculate DC bias on problem 6. And you've got to, you don't have to do it on problem 7. So it does show up all over the place. So doing the basic circuit analysis to handle these circuits is in there. We looked at MOS amplifiers, 4 different types: common source with a source resistor, common gate, and common drain, and some different biasing schemes. The 04 slides, we looked at the basic gain cell, which was a common source amplifier, and we added a current source load to it to increase the output resistance, which effectively increases the gain. We looked at the cascode as a common source, common gate combo. There is a cascode on this exam. It's a weird looking one, but it is a cascode. There's a cascode, there's a diff amp, there's a 3-stage amplifier, there's a single stage. Yeah, that's it. Cascode and diff amp, and a single stage amplifier. And we looked at those current mirror circuits and how they steer the current. 05, we looked at the MOS differential pair. It is the heart of most analog electronics, called an op-amp. Really important for analog, and it shows there's op-amps, differential pairs, and memory chips. There's differential pairs in the most digital of chips. ADCs and DACs, they're in there. Small signal operation, we looked at the differential and multi-stage amplifiers. So we'll go through a lot of this in more detail. Those are just the basic topics. Now, when you first look at a problem, and it's a circuit, you have to calculate the DC operating point. Don't panic. Think about the things you know, and this will be the next slides. Is there any place, look at the resistors. Are there any resistors that I know the resistance, I know enough information about the resistance, the voltage, and the current to calculate everything else? Go ahead and do that, because those are easy problems. It's just V equals IR. Voltage difference equals the current times the resistance. KCL and KVL. Is there any place on this circuit where I know 2 of the voltages going into a node and the only thing I don't know is the 3rd voltage? Can I apply these things easily? And KVL is a little bit harder to apply, so I maybe save that one for last. But go ahead and apply the simple things when you're calculating the DC bias. If the transistor's in saturation, and every transistor on this exam will be in saturation, you know the ID/VGS equation. If I know one of them, I can calculate the other one fairly simply. So that's another thing you can shoot for. And then write it down on the, once you figure out these pieces, write them down on the schematic. And that will help you figure out the missing pieces. Go back through the list again. And there are a bunch of numbers on page 1. So don't get locked up because you don't know the threshold voltage or you don't know VDD. Look at page 1. It's probably on there. This is the single stage amplifier summary. May or may not, is this going to help you out at all? There's people who just copy this down in their note sheet and they think they know everything. Oh, yeah, okay, so that's a cascode. That's a diff amp. This is, whatchamacallit? Oh, I know what that is. Yeah, it might help you out a little bit on one problem. In general, for the common source with source resistance, the cascode and the diff amp these look generally true. The only difference with these is it's a positive. The gain is positive. It's still GMRO. The input resistance is infinite, and the output resistance is RO in parallel with RD. You'd have to be able to look at the schematic and figure out, though, RD may or may not be a resistor. It may be the output resistance of a transistor. This diagram is amazingly useful. I would put it on your note sheet if you don't have it memorized. Somebody came up to me after taking this exam and said, I didn't think you were serious about that. But calculating ROs, how many times do you have to do it? You have to do it on problem 1. You have to do it on problem 4. You don't have to calculate anything on that problem. You have to do it on problem 6. And you have to do it on problem, no, you don't. Yeah, you do. You have to do it on problem 7. Yeah, 5 out of 7 problems involve you calculating ROs in some way or shape or form. So understand this. Looking into the gate, I always see infinity. Looking into the drain of the transistor, I see its output resistance times 1 plus the GM of that transistor times whatever resistance is hanging on the gate, on the source, and that will be, that's probably another transistor. Looking into the source, I see this, or I usually just use that form of the equation, 1 over GM.
And in this case, we're usually always given the RO of each transistor, right?
In all but one case, you're giving the RO of that transistor. And on one problem, you have to calculate the RO yourself using 1 over lambda ID or VA over ID. Okay, there is at least one point in the exam where you got to calculate GM and RO.
So just be sure to have that calculation on the note sheet.
Yes, and that will be on a slide coming your way fairly shortly. Yeah. You always assume it's in saturation. I may ask you to verify it's in saturation. To verify it's in saturation, you have to say VGS is greater than VT and VDS is greater than or equal to VGS minus VT. And the other form of that equation is this. And I'm not going to do, there's not a single problem on here where you have to calculate the bias point when I say like for max linearity, or I tell you the signal swing or anything like that, because that confuses people. There isn't a problem on here where I tell you to pick the bias point or to ask you what the signal swing limits are. What is the VG min and the VG max? Because those problems tend to confuse students way too much. But you may have, I don't know if this is on there or not. You may have to verify it's in saturation, but just assume it's in saturation in general. And if you know the current, you can calculate, you can calculate VGS. If I know VGS, I can calculate the current, and you'll be given the size of the transistors. We did do some homework problems where you had to calculate the size of the transistors. I'm not going to ask you to do that here. This is the small signal. This is what Sean was asking about. This is the small signal transistor model. Again, I have the ID equation. You may have to calculate RO. Let's look at the front page of the exam. We're given lambda in per volt. That's this lambda right here. This lambda right here is in micrometers, nanometers or something like that. So they're not the same thing. The one you're given on the exam front page is this one right here. And calculating GM, there are several ways to calculate GM. You can do it without knowing Kn. Remember, Kn is Kn prime W over L. You can calculate Kn without knowing the size of the transistor using this equation. You can calculate Kn without knowing the overvoltage by using this equation. I mean GM, sorry. GM with using this equation. So there's different forms of that, and they're useful in different applications. A lot of times people will come in and they've written one of these forms down and they can't calculate it because they don't know. Yes.
So we're referring to two different lambda in the RO equation.
Yes.
Which? I'm sorry,
The 1 over lambda ID, that lambda is in per volts. And the VA prime lambda L over ID, that lambda is in micrometers.
Oh, okay.
Yeah.
And then we're given the both.
On the front page, you're just given a lambda that's in per volts.
Oh, okay.
So that would be the one, that first equation would be the one I would recommend using. If you put the lambda in the other one, it's just not gonna, but you're also given VA too. Okay. Characterizing amplifiers. This is so basic that even digital engineers need to understand this, even if you're going to go off and be an FPGA designer. This is the amplifier right here. What we've been calculating through this whole unit is Rn, Rout, and gain. These three numbers. If I give you those three numbers, could you draw this picture? Cascade them, add a signal, and this is a signal source resistance. This is the voltage, the input signal itself. It has an output resistance associated with it too. That goes into the model, creates this voltage divider. It has a load. This is what's doing useful work. This is a motor or speaker or something like that. So can it drive that speaker, and can the signal source drive this amplifier? We expect to use this model on the exam. Can you tell me what kind of circuit it is? If part A of the problem is, here's an amplifier, can you tell me, is it a common source, what kind of amplifier it is? Can you identify it? A common drain has the input on the gate and the output on the source. A common source with source resistor has the input on the gate and the output on the drain. A common source has the input on the gate and the output on the drain. And a common gate has the input on the source and the output on the drain. My throat tickles right now. I may cough into the floor. You'll have 75 minutes to take the exam tomorrow. So the idea is you start between 1:30 and 2:15, and Chris has already signed up for it, and you have to be done by 3:30. If you start at 1:30, you have to be done at 245. Okay. Yeah. And only 3 people have signed up for the remote exam tomorrow already. The rest of you, I'm expecting to be in here. I sent you an email too. The body effect equation. Did I do that too? Yes, I did. There is at least one place on the exam you will need to use that equation.
Is there anywhere specifically one over in this section?
No, no, but everyone screws it up on the first exam, so I put it on the second exam. Is my general rule of thumb. If you don't know what the body, if you're given a transistor that looks like this, and there's no body connection whatsoever, you don't know what the body voltage is, you can ignore this. If you're given a transistor and it has a body tie on it, and you know this voltage here, then you have to take the body effect into consideration. People have been screwing that up the last several years. Okay.
And is this lambda the per volt, or is this?
It's not a lambda. This is a gamma.
Oh, okay.
And it is on the front page. It is gamma n, and it has units of square root of volts. And gamma p, depending upon if it's a PMOS. And that is on the front page. Okay. Figuring out these resistances. I don't think of them like this. They're not in series. If I have REQ2, this is looking into the drain of M1. There's no resistance at the source. So this is just going to be RO1. So looking in the drain of M2, what I see is I see RO2 times 1 plus GM2 times whatever resistance I see on the source, which is REQ2, which is RO1. Know how to do that. Again, it was like, what, 5 problems? Yeah, 4 or 5 problems on the exam will require you to calculate those ROs, those equivalent resistances looking into the gate, the source, and the drain. If it's looking in the gate, you say, yay, it's easy, it's infinity. So make sure you understand how to do this. It won't be anything where, there's generally not going to be a big, long, huge equation except for on one problem.
That's reassuring. I mean,
It's only one problem. I didn't do it over and over. It's nothing like the pre-lecture quizzes where you're looking into the drain of one and you see, and coming out of the source, you see like this explosion of 12 transistors or something like that. No, there's nothing like that. So this is a cascode amplifier. There is at least one cascode amplifier on here. There is another version of this called the folded cascode, and it's in the slides. And you may want to look at that one too. For the cascode, the advantage is my REQ looking down is so much bigger because it's multiplied like we did on the last slide. The gain of this is the gain of this transistor. The AV is GM big RO, and it's the GM of 1. And the RO is the output resistance looking through here, REQN. And if you have to calculate REQN, It's RO2 times 1 plus GM2 RO1. And you can do that if you can refer to that chart and understand how to use it. Not too terribly bad. Every one of these problems, most of these problems, except for the ones I've written, have easy parts to them. Make sure you get those easy points, because that makes the difference between, you know, having a grade you can recover from on this exam and having a grade that it's hopeless. I've had people make single digits on this exam, and it's just by not getting those easy points, turning in blank exams. I've had people make 110 on this exam. It just all depends upon, it goes back to those circuit analysis skills. V equals IR, can you do the basic circuit analysis? More so than being tricky problems. The problems are short enough that you should be able to do them in 10 minutes each. And that's if you have to really stop and think.
Why do we use GM1 to calculate gain?
GM1, because the transistor that contributes the most to the gain, this is a common, okay, so this is the input is on the gate and the output is up here on the drain. So this is a common source. This is a common gate amplifier. So it's a combination of a common source, common gate. And we went through and derived this at one point, but I can wave my hands and explain this. So the common source amplifier by itself has a gain of GM times its output resistance. And it's just the biggest contribution to the gain. The common gate, its gain, is that right? It's also GMRO. Okay, I can't make that argument anymore. Let me go back to where I was. Yeah, we derived that earlier, but that's the gain of the cascode. If you can add a chart with that in there if you need to, because there's two more in addition to this. If we go into this addition, if we go add the two others that we haven't put on this chart, there's the cascode, which has an input resistance looking into the gate of a transistor is infinity. Its voltage gain is GM big RO, and that's from it's GM of the common source transistor. And its output resistance is going to be, I'm trying to write this down and not screw you guys up too much. Its output resistance is the RO looking into V out. So you have to look at the circuit to figure out what that is. There's another type that's not on here too. It's a diff amp. And for a diff amp, the input resistance is infinity. The gain is GM of the diff amp transistor. Either one of them, they better be matched, times RO. And RO is again the RO looking into V out, which could be, you can pick either V out 1 or V out 2. They're going to be the same. And that was just basically these last two.
Okay, thank you.
So this is the, whatchamacallit, that's the cascode stage. Again, you might have to do some DC analysis on a circuit like this or the folded cascode. You may need to find the REQs and you may need to calculate the gain. The better you know that, the more automatic this is, the easier it's going to be for you. AB equals GM RO. The cascode current mirror, there is not a cascode current mirror on the exam. There's a regular current mirror at some point. Remember, that would just be we just take those transistors out and put this around here. The regular current mirror. Its resistance is the resistance looking into a single transistor, so it's going to be the RO. That's pretty much everything you need to know about current mirrors. And the current here, if the transistors are the same, the current here equals the current there. Sorry for the Baginskis now, I don't know why. They were evil though. I know, I understand now that this is hard to teach. Because it's almost like 188. I don't know, you got to learn the circuits. So we went through 3 different versions of this diff amp. The gain for all of these is GM1 or 2, you could pick either one, they're the same, times the output resistance, and the output resistance is looking in here. Okay. This first one has a resistor load. So this is an R load. This is called a current source load. Oh, thank goodness I took that for a mock exam. This one is called an active load. Is the difference. Now, if we look at these, they both have, all 3 of them have 2 inputs, BG1 and BG2. So all 3 of them are differential inputs. So my input is BG1 minus BG2, or VG2, it's the magnitude. I'll save myself a sign here and just make it the magnitude of VG1 minus VG2. If I look at the one with the resistor load, it's got 2 outputs. It has VD1 and VD2. So this one has a differential output. The iSource load also has a differential output. There too. The one with the active load has a single-ended output. There's only one output. So it's a little bit different in that respect. Now, if we want to think about which one gets used the most, think about this is the amplifier everybody wants. This has a differential input and it has a single-ended output. So this is the one we use for op amps and gets used everywhere, is the one with the active load. This one right here is the most commonly used one. This drain voltage is fixed by whatever the gate current is here. And this one can change. Okay. This is, oh yeah, this is another thing I haven't mentioned yet. Every exam I've ever given in here, except for maybe last semester, which is really weird, because I only gave 1 exam. I have asked you, given some random circuit, can you draw the DC bias circuit? So the DC circuit for this, I take out the AC sources. My AC sources are VID and negative VID. What else do I get to take out? There's no capacitors. Oh, yeah, capacitors matter. Let's write down the rules instead of trying to do it. Rules are more important. So DC circuit. What am I going to do? I'm going to deactivate the AC sources. And that means V sources are shorted. AC V sources are shorted, and I sources are open. And for DC, caps are open. So I do all that, and I've got my DC circuit, and I could redraw that. Okay,
And this applies to any of the amplifiers, not just the differential current.
yes. Though these are the rules that apply to everything. If there was a cap in here somewhere, then that cap becomes an open circuit. For the AC circuit, and I made you guys do this probably in 280, depending upon how apocalyptic your 280 class was. It's been a rough year and a half. We're going to deactivate the DC sources. So that means that the V sources get shorted out and the I sources get open. So in this example here, if I wanted to draw the AC circuit, this becomes an open circuit. So, oh, great. Oh, I was using the eraser, that's okay. This whole leg gets like taken out because it's an open circuit. This is a DC source up here. This is like VDD. So it gets shorted out, it goes to ground. My common mode source is a DC source, so that gets shorted out. And then the capacitors become shorts until we get to frequency analysis after this exam.
AC circuit is also just small signal, right?
Yeah, that's the small signal AC circuit. Now, if I want to take that's the AC circuit right here, but that's not the complete thing. What I have to do here is I have to put in the small signal model. So I have a gate, I've got a drain, and I've got a source. And this is my basic small signal model right there. This I can draw for anyone. And I'm only going to do the half circuit. So let's just do, and I'm not going to put a diff amp. You don't have to draw. You don't have to draw on the exam. This isn't a diff amp. This is GM, little VGS, and I've got my little RO right there. Now I look at the differential half circuit because this is like a virtual ground because they're tied together. What I'm seeing on the drain is I see a resistor called RD that's tied to an AC ground. On the source, I see this virtual ground right here. And on the gate, I see VID, and this is the AC half circuit. So put in the model, figure out what's connected to the gate, the source, and the drain with the sources deactivated, and you can do it.
Is it doing those to be parallel to
How could I make it not in parallel with RO? And let's just pretend for a second. If I had something like this, do you do that? Let's say this, I don't know if this is a real, I'm questioning my sanity here, whether this is a real circuit or not. But let's say I had something like this on the drain. Then it would be a series, resistor to the AC source. That's why I'm questioning my sanity. But you have to really look at the circuit and see what's there. Another common thing would be is maybe this is, maybe there's an RL here. I've got a load resistor there, and then it would be RD in parallel with RL. That's another that's a common variation. What I just drew is unless somebody's rookie mistake. But it could happen. What? Your gain is 0.1. It would, I actually, okay, don't laugh at this. I've seen people do stuff like this in real hardware, and you have to go in and like argue with them. I saw someone try to write a patent once for modulating the gain of a single transistor amplifier by changing the gate voltage. It nearly went through.
Oh.
I mean, it was like the patent attorneys were okay with it. They're okay with anything. They'll take $10,000. And they're going through. And finally, I just looked at one of the senior staff engineers, and I said, you know, hey, is this actually patentable to change the gain of a transistor by changing the gate voltage? Isn't this what transistors do? And he goes, oh.
It used to really pull the wool over their eyes, like a lot of jargon.
No, not really. It was just, it was the people doing this so poorly understood what they were doing that, and you're gonna be just amazed by that, by some of the people we work with. They so poorly understood what they were doing that they couldn't explain it well. And so a lot of times when you can't understand what somebody's saying, you tend to think they know more than they do.
Right, so they have jargon themselves.
Yeah. There was this one guy Paul was working with that he was writing a master's thesis, and his master's thesis was based on the fact that you could get gain out of a transmission line, but only if it was lossy.
Well, if you can't tell them the truth, baffling, yes.
And no, I mean it was perfectly mathematically correct, but what it relied on is that you had a lossy transmission line. It had a high series R, but that series R was negative. So there was no sense behind it whatsoever, and you see way more of that in the real world than you care.
You just built your line of Zener diodes and you're fine.
You just build it out of amplifiers. It's just, there's a lot more stupidity in the world than I care to talk about, even people who are highly educated. It is. Common mode rejection ratio. This is the only thing you will ever need to know about common mode rejection ratio for my exam. It's the differential gain over the common mode gain. Can you calculate it? Can you calculate it in dB? And be able to calculate all these gains, translate them into dB also. And it's that, and there's a whole lot more systems running on COBOL than you care to think about. and hard disk drives left in the world, and things that you just have to put up with it a little bit and modernize when you can. These are some problems from the last homework. If there's any questions about them or any other questions, I'm willing to take them now. We got about a half an hour. I'm going to check roll one more time. Victor is here. And again, the remote exam is tomorrow. Even if whether you've signed up for it or not. If you don't show up for one of the two exams, I don't have a sense of humor. Unless you've pre-arranged with me. There's one person who is pre-arranged to take the exam at a later date due to illness. Let's see, Sigwy, you're okay. You're not here. Oh, you are here. You're okay. You know when the exam is. It's Sigwy, Chris Weber, and Zach are the only people I have signed up to take the remote exam. And it is tomorrow, and it starts at 1:30. So you have to be there between 1:30 and 2:15, and finish by 3:30. Otherwise, you're in here, and that's on Thursday. Any questions? Don't get overwhelmed. If you look at a circuit, don't panic. There's probably at least one piece of this that is easy. Look for those easy parts and do them first. And once you complete the easy parts, the harder parts will kind of fall through. And stick with the basics. It's really not so bad. KCL, Ohm's law, you know the VGS, you know ID, you know VGS. If it is a diff amp, and you're doing a DC analysis of the diff amp, the only voltage input is the common mode voltage. So the current has to split equally between the two legs. It's not as complicated. The homework problems are harder. It's not nearly as complicated as the homework problems. Yeah. If you understood the homework, you're gonna. This isn't so bad. Okay. Oh wait, I saw you. I'm not checked off. Okay. People who are not here are Danielle, or one person I know about. Okay. All right. No questions. I will be in my office tomorrow. What's tomorrow? Wednesday? Yeah. You can always ask when the online exam is, if you forgot to sign up for it. Okay.
So
Okay.
you could come in and ask questions, just not during the exam. Not online.
Yeah, you can ask me questions. I will be in probably around 10ish. So you can always ask me questions by email, and you can ask me questions by email. You can ask me questions during my office hours Zoom, and I may reply by email. Okay, depending upon how okay. And there's people asking me questions during the exam too. Some of those I answer and some of those I don't. Okay. You guys okay? Okay. Study.
Yeah.
It's harder than exam one. And the reward is you do well on this one, and you've turned in all your labs, and you've done all, you have a fairly good grade in here, then you don't have to take the final, which is harder than exam two. I had these horrible electronics teachers at Auburn. They were just evil. I mean, they would take this and they would like twist it on the exams, and no one could do it, and then they just fail everybody. Yeah. Okay. I don't know. Yeah, it's okay.
You will not be affected by this problem.
Why? Wait.
Oh, is it a computer engineer? Is it some? Okay, never mind.
You don't want to know.
Okay, I don't want to know.
You don't want to know.
Okay, yes, I've learned what?
Is it what I think it is?
Yeah, it's exactly what
I am the only one out of the sleep, but there's only 5 people in this room.
Oh, I'm stupid too.
There's family of the burden, you're welcome.
Okay, I said if there's no questions, I'm gonna cut the recording, and remember to show up for the exam.